What are alternating current capacitors and their functions? Alternating current, AC, capacitors are electronic components designed to store and release electrical energy in alternating current circuits. Capacitors are passive components consisting of two conductive plates separated by an insulating material known as a dielectric. When a voltage is applied across the plates, an electric field forms in the dielectric, causing it to store electric charge. Alternating capacitors, also known as AC capacitors or motor-run capacitors, are specialized capacitors designed to be used in alternating current AC circuits. These capacitors are typically found in various electrical devices and systems, including motors, pumps, compressors, and air conditioners. The primary function of alternating capacitors is to improve the power factor of AC circuits. Power factor is a measure of how effectively electrical power is being used in a circuit. In AC circuits, the power factor can be affected by the phase relationship between the voltage and current. Capacitors can help correct this phase shift by supplying reactive power, which can cancel out the reactive power drawn by inductive loads such as motors. By improving the power factor, alternating capacitors can increase the efficiency of electrical systems. By reducing reactive power, the overall power usage becomes more efficient, leading to reduced energy consumption and lower electricity bills. Reduce voltage drops and line losses. Improving the power factor can help minimize voltage drops and line losses in electrical distribution systems, which can improve the overall performance of the system. Improve motor performance. In systems with motors, alternating capacitors can help improve motor efficiency, reduce overheating, and extend motor lifespan by providing the necessary reactive power to compensate for inductive loads. Comply with utility regulations. Some utility companies may impose penalties or charges for low power factor, so installing alternating capacitors can help businesses avoid these penalties and ensure compliance with regulations. Overall, alternating capacitors play a crucial role in optimizing the performance and efficiency of AC electrical systems, particularly in applications where inductive loads are present. In AC circuits, capacitors have several functions. Power factor correction capacitors, also known as power factor correction (PFC) capacitors or power factor correction banks, are specialized capacitors used to improve the power factor of electrical systems. They are installed in parallel with inductive loads in AC circuits to counteract the reactive power drawn by these loads, thereby improving the overall power factor of the system. Here are some key features and characteristics of power factor correction capacitors. Purpose. The primary purpose of power factor correction capacitors is to improve the power factor of electrical systems. Power factor is a measure of how effectively electrical power is being used in a circuit. In AC circuits, the power factor can be affected by the phase relationship between the voltage and current. Inductive loads, such as motors and transformers, draw reactive power, which can lower the power factor. Power factor correction capacitors provide reactive power to offset the reactive power drawn by inductive loads, resulting in a higher power factor and improved efficiency. Construction. Power factor correction capacitors are typically constructed using metallized film or electrolytic dielectric materials, depending on the application and requirements. They are designed to handle the continuous voltage and current stress associated with power factor correction applications. Capacitance value. The capacitance value of power factor correction capacitors is selected based on the reactive power requirements of the system and the desired power factor improvement. Capacitance values typically range from a few microfarads, F, to several hundred microfarads. Voltage rating. Power factor correction capacitors are rated for specific voltage levels to ensure safe and reliable operation in electrical systems. Common voltage ratings range from 240 volts to 690 volts AC, depending on the application and system requirements. Mounting. These capacitors are designed for easy installation in electrical systems. They may be installed in capacitor banks, which consist of multiple capacitors connected in parallel and housed in a common enclosure. Capacitor banks are typically mounted in electrical switchgear rooms or on electrical panels. Usage. Power factor correction capacitors are commonly used in various industrial, commercial, and utility electrical systems to improve power factor, reduce energy losses, and optimize system efficiency. They are particularly beneficial in systems with large inductive loads, such as motor-driven equipment, transformers, and fluorescent lighting. Safety. It's essential to use power factor correction capacitors that meet safety standards and regulations to ensure reliable and safe operation. Capacitors should be properly sized, installed, and maintained according to manufacturer guidelines and electrical codes to prevent overvoltage, overcurrent, and other potential hazards. Overall, power factor correction capacitors play a crucial role in optimizing the performance and efficiency of electrical systems by improving power factor and reducing energy consumption. They are essential components in power distribution networks, industrial plants, commercial buildings, and utility infrastructure. Motor-run capacitors are a specific type of capacitor designed for use in alternating current (AC) motors. They are commonly used in single-phase induction motors to improve the power factor and performance of the motor. Here are some key features and characteristics of motor-run capacitors. Purpose. Motor-run capacitors are used to provide a phase shift between the voltage and current in the motor windings, thereby improving the power factor of the motor. This helps in increasing the motor's efficiency, reducing power losses, and improving its starting torque and running performance. Construction. These capacitors are typically constructed using metallized film dielectric materials to withstand the continuous voltage and current stress associated with motor operation. They are designed to have a long operational life and are often housed in cylindrical or oval-shaped metal or plastic cases for protection. Capacitance value. The capacitance value of motor-run capacitors varies depending on the motor's design and requirements. Capacitance values typically range from a few microfarads, F, to several tens of microfarads. Voltage rating. Motor-run capacitors are rated for specific voltage levels to ensure safe and reliable operation in motor circuits. Common voltage ratings range from 250 volts to 450 volts AC. Mounting. These capacitors are designed for easy installation in motor circuits. They may have mounting studs or terminals for connection to the motor terminals, and they are often mounted directly on or near the motor housing. Usage. Motor-run capacitors are commonly used in various applications, including HVAC systems, refrigerators, air compressors, pumps, fans, and other single-phase induction motor-driven equipment. Safety. It's essential to use motor-run capacitors that meet safety standards and regulations to ensure reliable and safe operation. Capacitors should be properly sized and installed according to manufacturer guidelines and electrical codes. Overall, motor-run capacitors play a crucial role in enhancing the performance and efficiency of single-phase induction motors by improving their power factor and running characteristics. They are essential components in various electrical and mechanical systems that rely on AC motors for operation. Oil-filled capacitors are a type of capacitor where the dielectric material, which separates the capacitor's plates, is impregnated with or immersed in an insulating oil. These capacitors are commonly used in high-power and high-voltage applications where stability, reliability, and long service life are critical. Here are some key features and characteristics of oil-filled capacitors. Dielectric material. The dielectric material in oil-filled capacitors is typically a paper or plastic film that is impregnated with insulating oil. The oil serves as both a dielectric and a coolant, providing excellent heat dissipation and allowing the capacitor to operate at higher temperatures. Construction. Oil-filled capacitors consist of two conducting plates separated by the oil-impregnated dielectric material. The assembly is typically housed in a metal or plastic casing to provide mechanical protection and insulation. The casing is hermetically sealed to prevent leakage of the oil and to maintain the integrity of the capacitor. Capacitance. Oil-filled capacitors can have a wide range of capacitance values, ranging from a few picofarads to several hundred microfarads. The capacitance value is determined by the size and geometry of the plates, the dielectric material, and the oil used. Voltage rating. Oil-filled capacitors are designed to handle high voltage levels, making them suitable for high power and high voltage applications. Voltage ratings can range from several hundred volts to tens of thousands of volts, depending on the specific application requirements. Cooling. The oil used in oil-filled capacitors serves as a coolant, dissipating heat generated during operation and maintaining stable operating temperatures. This allows the capacitor to operate reliably in high-power applications without overheating. Applications. Oil-filled capacitors are commonly used in a variety of high-power and high-voltage applications, including power transmission and distribution systems, electric utility substations, power factor correction systems, motor starting and running capacitors, and high-frequency filtering circuits. Reliability and longevity. Oil-filled capacitors are known for their reliability and long service life, often lasting for decades without significant degradation in performance. The use of high-quality materials and construction techniques, along with the cooling properties of the oil, contribute to their durability and longevity. Maintenance. While oil-filled capacitors are generally reliable, periodic maintenance may be required to ensure proper operation and prevent failures. This may include checking for leaks, monitoring oil levels and condition, and performing electrical tests to verify capacitance and insulation resistance. Overall, oil-filled capacitors are essential components in high-power and high-voltage electrical systems where stability, reliability, and long service life are crucial. Their robust construction, high voltage ratings, excellent heat dissipation properties, and long-term reliability make them well-suited for demanding applications in various industries and sectors. Variable capacitors, also known as tuning capacitors or trimmer capacitors, are capacitors whose capacitance value can be adjusted manually or electronically. These capacitors are used in electronic circuits where the capacitance needs to be varied to tune or adjust the frequency response of the circuit. Here are some key features and characteristics of variable capacitors. Construction. Variable capacitors typically consist of two sets of metal plates separated by a dielectric material. One set of plates is fixed, while the other set is movable. By adjusting the distance between the movable and fixed plates, the effective capacitance of the capacitor can be varied. Capacitance range. Variable capacitors can have a wide range of capacitance values, from a few picofarads to several hundred picofarads or more. The specific capacitance range depends on the size, geometry, and materials used in the construction of the capacitor. Adjustment mechanism. Variable capacitors can be adjusted manually using a knob or dial, or electronically using a voltage or current signal. Manual adjustment is typically achieved by rotating a shaft connected to the movable plates, while electronic adjustment involves applying a control signal to change the capacitance value. Applications. Variable capacitors are commonly used in radio frequency (RF) circuits, such as tuners in radios, televisions, and communication systems, to adjust the resonance frequency and select different channels or frequencies. They are also used in oscillators, filters, and impedance matching circuits where precise tuning of the capacitance is required. Types. There are several types of variable capacitors, including air variable capacitors, vacuum variable capacitors, and ceramic variable capacitors. Air variable capacitors use air as the dielectric material and are suitable for low to moderate capacitance values. Vacuum variable capacitors use a vacuum as the dielectric and are used in high-power RF applications. Ceramic variable capacitors use ceramic materials and are often smaller in size but have limited capacitance range compared to air variable capacitors. Frequency stability. Variable capacitors should be selected based on their frequency stability, which refers to how stable the capacitance value remains over different environmental conditions such as temperature and voltage variations. Capacitors with higher frequency stability are preferred for applications where precise tuning is required. Temperature coefficient. The temperature coefficient of variable capacitors indicates how much the capacitance value changes with temperature variations. Capacitors with a low temperature coefficient are preferred for applications where stable capacitance values are required over a wide temperature range. Overall, variable capacitors are versatile components used in electronic circuits to adjust the capacitance and tune the frequency response of the circuit. They are essential in RF applications and other circuits where precise tuning is necessary for optimal performance. Filtering with capacitors in AC circuits involves using capacitors to smooth out voltage fluctuations or remove unwanted noise from the signal. This is commonly achieved by creating low-pass or high-pass filter circuits. Low-pass filter. In a low-pass filter configuration, the capacitor is connected in parallel with the load, such as a resistor, across the output of the circuit. This arrangement allows low-frequency signals with frequencies below a certain cutoff frequency, to pass through the capacitor while attenuating or blocking high-frequency signals. Low-pass filters are used to eliminate high-frequency noise or ripple voltage from power supplies, audio signals, and other applications where a smooth, constant voltage is desired. High-pass filter. In a high-pass filter setup, the capacitor is connected in series with the load. This configuration allows high-frequency signals with frequencies above a certain cutoff frequency, to pass through the capacitor while attenuating or blocking low-frequency signals. High-pass filters are used to remove low-frequency noise or DC offset from signals while allowing higher-frequency components to pass through. The cutoff frequency of the filter, the frequency at which the filter starts to attenuate the signal, is determined by the values of the capacitor and any other components in the circuit, such as resistors or inductors. By selecting appropriate values for the capacitor and other components, engineers can design filters that effectively remove unwanted frequencies from AC signals, resulting in cleaner, smoother output waveforms. In the context of energy storage, capacitors in AC circuits can store electrical energy temporarily and release it when needed. This property is particularly useful in various applications where a rapid discharge of energy is required, such as in power supplies, flash units in cameras, and energy storage systems. Here's how energy storage with capacitors works in AC circuits. Charging. When a voltage is applied across the plates of a capacitor in an AC circuit, the capacitor starts to charge. During the positive half-cycle of the AC waveform, the capacitor charges up as current flows through it. The charging process continues until the voltage across the capacitor reaches its peak value, which is determined by the amplitude of the AC voltage. Discharging. During the negative half-cycle of the AC waveform, the voltage across the capacitor decreases as the polarity of the AC voltage reverses. The stored energy in the capacitor is then released back into the circuit as current flows out of the capacitor. This discharge process continues until the voltage across the capacitor reaches its minimum value, which is typically zero. Energy storage and release. Capacitors store electrical energy in the form of an electric field between their plates. The amount of energy stored in a capacitor is proportional to the square of the voltage across it and is given by the equation E equals 1/2 *C* V squared, where E is the energy stored, C is the capacitance of the capacitor, and V is the voltage across the capacitor. When the capacitor discharges, this stored energy is released back into the circuit as electrical current. Energy storage with capacitors in AC circuits is advantageous in applications where fast energy discharge is needed, such as in pulse power systems, power factor correction, and voltage regulation circuits. Capacitors offer high power density, low internal resistance, and rapid response times compared to other energy storage devices like batteries. However, capacitors typically have lower energy storage capacity compared to batteries and are often used in conjunction with other energy storage technologies to meet specific requirements. Coupling and decoupling with capacitors in AC circuits are important techniques used to control the flow of signals between different stages of a circuit and to prevent undesired interactions between components. Here's a breakdown of how coupling and decoupling with capacitors work. Signal coupling. In many electronic circuits, signals need to be transferred from one stage to another while blocking any DC component that might be present. Capacitors are commonly used for this purpose because they block DC while allowing AC signals to pass through. When capacitors are used for signal coupling, they are typically placed in series with the signal path. This setup ensures that the DC bias is isolated and only the AC component of the signal is transferred to the next stage of the circuit. Signal decoupling. In complex electronic systems where multiple components share a common power supply, variations in current demand from one component can affect the voltage levels seen by other components. This phenomenon, known as power supply ripple or noise, can lead to undesirable behavior or interference in the circuit. Capacitors can be strategically placed across the power supply lines of individual components to act as decoupling capacitors. These capacitors store charge and act as local reservoirs of energy, supplying additional current to the component when needed and thereby stabilizing the voltage levels. By reducing the impact of power supply ripple, decoupling capacitors help ensure proper operation and prevent unwanted interactions between components. Overall, coupling and decoupling with capacitors play crucial roles in maintaining signal integrity, isolating components from DC bias, and minimizing power supply noise in AC circuits. These techniques are widely used in various electronic systems ranging from audio amplifiers and radio receivers to digital circuits and microcontrollers. Proper selection and placement of capacitors for coupling and decoupling are essential for achieving optimal circuit performance and reliability. Motor start and run capacitors are specialized capacitors used in alternating current (AC) motors to facilitate their starting and running operations. These capacitors provide additional phase-shifted currents to the motor windings, aiding in the motor's starting torque and ensuring smooth operation during the running phase. Here's how motor start and run capacitors function. Start capacitors. Start capacitors are used primarily in single-phase AC motors, which require an initial burst of energy to overcome inertia and start rotating. When the motor is switched on, the start capacitor is connected in series with the motor's start winding for a brief period, typically a few seconds, to create an artificial phase shift between the start and run windings. This phase shift generates a rotating magnetic field in the motor, producing the necessary starting torque to initiate motor rotation. Start capacitors are designed to have a high capacitance value and are usually electrolytic capacitors, capable of handling the high current surge during motor startup. However, they are not intended for continuous operation and are disconnected from the circuit once the motor reaches a certain speed.